Yeah, thank you for the nice introduction. And today I would like to talk about my PhD research, solving Row-Sparse principal component analysis for Convex integer program. And this is a joint work with my PhD advisor, Santanu S, and one of my co-authors, Molinaro. Okay. Yeah. Okay, so let's first introduce the background. What is sparse principal component analysis, or what is the principal component analysis problem? So it is the following. I give you a sample covariance matrix A, and the principal component analysis problem is to find out the top leading principal components. And the principal components in linear algebra, you could think it as the eigenvector. And it denotes like this. I give you a large sample covariance matrix, and now you would like to find, like, for example, I equals to 3, the top 3 leading principal components. Okay, so it is a very good dimensionality reduction tools in scientific data analysis. I mean, the sparse PCA, the original PCA problem, for example, in some quantitative finance. And also you could think it also have some applications in biology. And however, it has a very obvious drawback. The problem is, if you consider in some high dimensional settings, the principal components that you obtain from the original PCA problem, that most of its components are non-zeros. And each of the components corresponding to one feature of what you want to consider. So there becomes a large combination of a lot of features, and you do not understand what it is. So therefore, in order to enhance the interpretability, you need to add additional constraint. So the constraint is the so-called the sparsity. So if we have the sparsity constraint, we shrink or we force that the number of features that we want to consider is upper bounded. And therefore, for example, if I consider some principal components in 1,000 dimensions, and then now I just force it to say, okay, and I only request you to have a principal components with at most 10 features, then you could somehow interpret what it is. And here is the formal definition of this. The simple covariance matrix A is the same, and also it should satisfy the ordinality constraint, which is the second constraint. And there's one additional constraint that we added is this zero norm constraint, which denotes in this work, the number of non-zero rows of V. So here is an illustration. I give you the covariance matrix, but I tell you that I only want to at most 4 rows, which is non-zero. So of these 4 rows are non-zero, and the rest of them are zeros. We just, if we consider the objective function value, the rest of part we do not need to think about. We just ignore them. So this is the definition of sparse PCA problem. And before I present my main contributions or what I did, so let's first go through some existing methods and the result. It is a well-studied problem, and the existing methods and the result can be generally classified into 4 categories. The first one is some statistical result. The main core idea is that if the sample covariance matrix or each of the sample are generated from some underlying distributions, then statisticians have some algorithms or have some ways to get good estimation of the underlying model, which I mean is have good performance but they should under statistical assumptions. And the second category is some very efficient heuristics. But the drawback is that they do not have any guarantees. And for the third one, which is some kind of ADMM type algorithm, this type of algorithm converges to guarantee. That's very good. But the problem is that they somehow they change or transfer the original sparse PCA problem into some regularized with some regularized term on the objective function. And the final one, which is the Sdp relaxation, I think it is a very good type of technique, and it can solve the sparse PCA problem very directly. The problem is that since we want to do the Sdp relaxation, we need to consider the product of the original variable space. So we lifting the number of variables from n to x. Let's say if we have n variables, we need to lifting it to n squared. So therefore, it's hard to scale to some large instances. So based on the existing methods, what we want to do is we want to find a framework that both verify or guarantee the quality of any primal feasible solutions, and also we want to solve it. We want to check it in a tractable time. Yeah. 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 The regularization is somehow like you have this this nonlinear constraint, and they do not they cannot deal with it directly. What they did is they just put this as a penalty onto the objective function, and then do some type of ADMM algorithm and solve it. And then they say that after they solve this regularization type algorithm, it converges, but the solution that it obtained is not a feasible solution of the original problem. So, okay, so this talk can be generally separated into three parts. The first part is dual bounds. We show we propose an efficient framework that finding dual bounds of the sparse PCA problem. And primal bound is that we also design a primal feasible iterative algorithm, which gives you a good primal feasible solutions. And finally, some numerical result to demonstrate that the efficiency and the of our method. So, okay, let's first go to the dual bound. So recall that we want to verify the quality of any primal feasible solution. So the first question is, what is the quality of a given primal feasible solution? A very natural idea is to check how far it is away from the optimal. So if this delta quality is small enough, then we could say that, okay, now the primal feasible solution that you give to me is good enough. But here's a problem. The optimal value of sparse PCA problem is NP hard to approximate. Then what we need to do? A very natural idea is that, okay, instead of solving or exactly finding out the optimal value, we consider the relaxation and we find a bound on the optimal value. So here's the high level idea. We have a feasible solution V, and we start here, and we want to compute the delta quality for the optimal value. And now, okay, we can do it. We try to consider the relaxation of the original problem. And then since the relaxation of this original problem, we have a convex relaxation. Then due to the strong duality, the convex relaxation is equal to the dual of the convex relaxation. And then one step further, in some of the cases, we even do not need to optimize that dual. We just find any feasible dual solution, which is an upper bound of this guy. Then that's enough. So instead of exactly computing the delta quality, we want to consider this delta estimated quality as the upper bound to get to estimate the quality of primal feasible solution. So any questions? So what we want to do now is we want to build a convex relaxation of sparse PCA problem. And let's check the original sparse PCA problem. As we can see that it has two non-convexity parts. The first part is obviously the feasible region is not convex because it has orthogonality constraint and also it has discrete cardinality constraint. And for the objective, it is also not convex because it is maximize a convex function. So maximizing a convex function is not a convex. We need to consider something to deal with the objective also. So in what follows, we first propose the convex relaxation of the feasible set, and then we convexify the objective. So how to do the convex relaxation of the feasible region? Here's one of our main contributions. What we did is we consider this orthogonality constraint, and then we relax it by upper bounding the operator norm of the V matrix. And similarly, and then because we have the row sparsity constraint, the number of non-zero rows of the principal components are at most k. And in this case, we consider the L2 to 1 norm of this V matrix, and we obtain the second constraint of this. And finally, since the sparsity of the row sparsity of the principal components at most k, then we could consider the summation of the L2 norm of the row of V matrix. And it is upper bounded by the square root RK. So, okay, you may want to say that, okay, now we obtained a convex set, this one, CR1, I think. And also we know that the convex relaxation of the F, convex whole FF is contained in this set. Then what we could say anything more about this CR1 set. So we show that this convex relaxation has a provable approximation guarantees. And the first theorem of this, it says that if we replace the original convex whole of the feasible region F by this convex relaxation CR1, what we obtained is a multiplicative approximation ratio on the objective function value. And formally speaking, it says that the opt CR1 is lower bounded by opt F and upper bounded by some approximation ratio square times the opt. And this is one of the main theoretical result of this work. And due to the time limit, I will not go into the detail of the technical detail of how to prove this algorithm. But the only thing you need to know is that, okay, the convex set we obtained, has some theoretical guarantees of the original convex whole. Okay, so I will skip these slides. And now, the second thing you would like to ask is the following. So, okay, now we obtained the convex relaxation CR1 of the original feasible set F. But you may ask that, okay, the operator norm and the L21 norm are somehow hard to code and scale in practice. because the operator norm, you need to use the Sdp relaxations, and L2 to 1 norms that you also need Sdp. You also need Sdp constraint to approximate. So I do not want Sdp in the constraint or in the optimization, because it's hard to scale to large instances. So what I need to do is we further relax the CR1 into this convex set CR2. And what we did is we just greatly relax the operator norm part, and also relax the L2-1 norm part. And for the final constraint, the summation of L2 norm of rho, we just keep it remains the same. So okay, we obtained the second relaxation. And similarly, the second relaxation also has an approximation ratio guarantee for the convex hull, for the original convex hull. And formally speaking, it looks like this. And it is upper bound. The approximation ratio is upper bounded by 1 plus square root. Okay. And yeah, I also want to skip this, the proof of this theorem. Okay, so far, now we obtain the relaxations, the convex relaxations of the feasible set, and then we need to convexify the objective function. So what we did is a very straightforward way. We reformulate the objective function into the summation of squares. And and for each of the square term, we just we consider a piecewise linear approximation like this. The blue part is the quadratic, the squared part, and the orange part is the piecewise linear upper approximation for the quadratic. So it's like this, and we implement this using the SOS type 2 constraint. So, I mean, special ordered set type 2, and it is defined here. So, any questions? Okay. Let's move on. Okay, now if we combine these two techniques together, now we obtain a convex. We obtain a convex relaxation of the original sparse PCA problem, and we call it the convex integer programming because the SOS type 2 constraint requires additional integer variables. I mean binary variables to formulate these piecewise linear terms. So now it goes to our second theoretical result. It says that if we do this kind of convex relaxation, then the optimal, the original optimal value is upper bounded by the optimal value of the convex relaxation, which is trivial, and also upper bounded by this guy. The first term, which is the convex relaxation of this problem, which is upper bound, which as we show is upper bounded by some approximation ratio times the optimal value of the original sparse PCA problem, and add some this additive term. And I would like to point out this n in red because this n is the number of piecewise linear units that you want to use in SOS type 2 constraint. And this capital N is somehow you could predetermined before you solving the before you solving this convex integer programming. And this additive arrow is involved because we use this SOS type 2 piecewise linear approximation. Any questions? Okay, now in previous part we obtained we obtain good convex dual bonds. And now we would like to consider how to obtain good primal bonds. So before we talk about how to find the primal bonds for this Row-Sparse PCA problem, a good news for the original sparse PCA problem. I mean, if we only want to find the top one principal component, there are a lot of many very efficient algorithms to do that. And for this specific problem, if set R equals to 1, then finding a good primal feasible solution is very efficient. But it's very efficient. And for this case, and for this case, in order to find a good primal feasible solution, it is equivalent to consider which rows you want to make it to be non-zeros. So in the same idea, you would like to decide which support set you would like to pick up. So if you fix one of the support set S, then what you want to do is you just the only thing you need to do is you do eigenvalue decomposition on the sum matrix of the sample covariance matrix, and you just pick out the top R leading eigenvectors, and then you are done. So the hard part or the challenging part is how to find a good support set. So naturally, there is a naive local search algorithm to do that. What we did is, okay, we start from some set S0, and in each of the iteration, we just remove one of the row in current support set and add another row into our set. And then we check all the possible this switch and look and find the largest one, and then we make one step update. However, this is not very efficient, especially in large size, because we could see that we need to search for all the k times d minus k possible neighborhoods. That d is the dimension of this principal component. And also, and that means we need to do k times d minus k eigen computations in each of the sum matrix. So it is it's not good, and we want to improve the efficiency. What we did is, and we want to avoid these so many eigenvalue computations. So what we did is we consider somehow more sophisticated way. So here it is. What we do is in each of the step, for the current support set, for each row, we compute one of the value which corresponding to each row as a tester or an estimator of how important this row it is. And similarly, for the rows that's not in current support set, we also compute a value to denote how the weight of this current of the row that's not in the support set. And then we do a switch. To remove the most not important row in current support set and put one row which has the largest importance, which are not in current support set. And after we do that, then we make a switch and update the current support. So therefore, using this kind of local search, we only need to do one eigenvalue decomposition, and which greatly improves the efficiency. So yeah, these are two properties of the efficient local search algorithm that we proposed. One is, okay, it is monotone because each of the switch we guarantee the monotone increasing of the objective function value. And also since they are And also it will be terminated in d times you choose a if close because it at most d choose k possible supports in a given if you fix the dimension narrative. Okay, so we have a good way to find out primal feasible solutions, and here are some numerical results. So we compare the convex integer programming upper bounds verification with this following dual bounds baseline. The first one is very straightforward. We just consider the summation of the diagonals of the top k largest components, and the second one is the Sdp relaxation of the original problem. So here's the setting. We compute the primal solutions based on our local search method, and we test these following instances. You can see that it's 500 times 500 matrix, and the largest one is the 2000 size matrix. So as you can see that based on the comparison, the convex integer programming method outperforms the baseline 1, and for the baseline 2, the Sdp relaxation. A very important point I would like to point out is that if it goes to the 500 size matrix, the Sdp relaxation requires too much space complexity, and it cannot be solved it cannot be solved in my MacBook. And if we shrink down the size of the matrix to like 100 size, the gap between the Sdp relaxation and the convex IP are somehow comparable. Okay, so these are the numerical results. Is there any questions? Maybe you. Okay.
So, with 500 instances, the Sdp relaxation doesn't solve.
Yeah, it doesn't solve. Yeah. If
Or,
you scale down to like 100 case, it can solve within time limits, and also.
So 500 is the hard.
Yeah.
Hard. Any other questions?
Okay, so these are future directives. Thank you. Okay. Yeah.
So your final heuristics depend on the relaxation. Do I understand that they are separate?
Yeah, there are two separate algorithms. The primal does not depend on the dual algorithm.
And you leverage the relaxation results.
Leverage the dual without primal. Yes, you can do, but you can do that. So every time you got a dual bound, it's a dual bound for the whole sparse principle, sparse PCA problem. And the primal is something that you just obtain in another independent algorithm. Yeah. This one? Oh yeah, this is the gap. This is the estimation quality divided by the lower bound. The lower bound is obtained from a feasible primal solution. This one? What you want to ask? Could you? It's a 2000. The largest instance that we consider is 2000.
And so the number of what size, real size.
Oh, the time. Oh, the time for yeah. So the time for the 500 takes 2 hours, and it takes about 3.5 hours to 2000. Yeah. For the literature, for Sdp for Sdp, it cannot be solved within this time. Yeah.
And lower bound is a single solution that is computed. Like for the gap, you measure the performance by the quality.
Yes.
Data,
yeah.
And divided by LB. So LB is computed from your approach.
Yeah, the LB is computed from at the lower bound of the sparse PCA because this V is a feasible primal solution. So you want to maximize the sparse.
Yeah, I was thinking measure fine because I know like you're not comparing the gap, right? You're comparing something for data or only the data.
Yeah, this delta quality is the distance between your lower bound and your estimated upper bound. Yeah.
Well, we can take many other questions of fine and internet. So thanks to Guanyi, thanks Simon for taking the talk today. And